Welcome to Part C of Unit 6 for our course on statistics.
So up to this point, I've been talking about examples where I'm comparing just two groups, which would be an example of a simple contrast, a contrast between just two groups, or a focused contrast, a contrast I could compare two groups that I hold on two hands. But this unit is a unit about making multiple contrasts. This unit is about situations where we have more than two groups. So how do we handle that? What if we have, say, maybe we have two different treatments and a control group? What if we have more than two groups? What we're going to need to do in the situation is to create multiple contrasts to address the fact that we have more than two groups. And the approach we're going to take to creating multiple contrasts is to do this thing called planned comparisons or planned contrasts. Say, for example, I'm doing my study where I have students that are sad because they're ending their statistics course and they're experiencing that statectomy sadness. And I'm wanting to test different treatments that we might use to make people happier, to make the students happier so they're not quite so sad after ending their statistics course. So say I do a study where I get a sample of students that are experiencing some statectomy of sadness, and some students get randomly assigned to a control group where they don't get any treatment, and another group of students get randomly assigned to receive my wonderful green happy gas aromatherapy treatment. But maybe I also have, maybe I'll call this an enhanced treatment. Some students get both the aromatherapy plus they get lots of coffee to drink. So one set of students get a treatment that's just called aromatherapy, the basic aromatherapy treatment. And another set of students get the enhanced treatment, the aroma plus coffee therapy. So now I've got three groups. I've got the control group, the aromatherapy group, and the aroma plus coffee group. So I've got a sample of students. They're all experiencing some statectomy sadness. And I randomly assign those students to three groups. Some are in the control group, some are in the regular treatment, aromatherapy, and some are in the enhanced therapy, the aroma plus coffee therapy. And I want to see if there's a difference between these three groups in their levels of happiness at the end of treatment. So let me first show you how I will address the situation, and then I'll go back and provide some details on exactly why I did the things that I did. So as we're going along here, it's possible you might have some questions like, now, why did he pick those values? But hold on to those questions. I'll answer those eventually. So what I'm going to do, if I have more than two groups, say I have group 1 as my control group, group 2 gets the regular treatment, group 3 gets the enhanced treatment, and I randomly assign people to these three groups, and then I'm looking at I want to test for possible differences between these three groups and their levels of happiness at the end of treatment. And so I have more than two groups. So what I'm going to do is to create multiple contrasts. And the number of contrasts that I'm going to create is going to be equal to the number of groups minus 1. That is, that's the number of contrasts that are free to vary. We actually saw that before in our previous video, and we're actually going to create the number of contrasts will equal number of groups minus 1. So if I have three groups, it means I'm going to create two contrasts. And for each contrast, I'm going to assign a different set of numerical values to people based on group membership. So here I have this chart here, and I have x1, and x1 is going to be a variable, and that's going to be the first contrast. And I'm going to assign people values on x1 based on group membership. And here's what I'm going to do. I'm going to say if you're in group 1, your score for x1 is going to be negative 0.66. If you're in group 2, your score for x1 is going to be positive 0.33. And if you're in group 3, your score on x1 is also going to be positive 0.33. So now I've just assigned people, I've done coding. So this is a coding process. I'm assigning values to people based on group membership. But now I'm not just using these zeros and ones. I've got these other numbers, which I'll explain where these are coming for eventually. But what I'm doing is I'm saying if you're in group 1, your score on x1 is negative 0.66. If you're in group 2, your score on x1 is 0.33. And if you're in group 3, your score on x1 is 0.33. And then I'll create the second contrast, the second x variable. So each contrast is an x variable, and each x variable is created by assigning numerical values to people based on group membership. And for x2, my second contrast, I'm going to say if you're in group 1, your score is 0 on x2. If you're in group 2, your score is negative 0.5. And if you're in group 3, your score is positive 0.5. So now everyone has a score on x1 and everyone has a score on x2. I've created two variables, x1 and x2. And each of these variables is a contrast. x1 is a contrast and x2 is a contrast. And each contrast was created by coding, by assigning numerical values to people based on group membership. And this chart that I have right here could be called a code assignment chart. It's just clarifying what values get assigned to people in what group, what values for x1 get assigned to people based on group membership, and what values get assigned to people for x2 based on group membership. So the code assignment chart just clarifies what values get assigned to which people for which variables in which group. So that's the process of creating two contrasts. When I have three groups, I create these two contrasts for x1 and x2. Now that I've created these two contrasts, which are two x variables, I'm going to take these two x variables, x1 and x2, and put them into a multiple regression equation. So if the outcome variable, say, is levels of happiness, if y is my outcome variable, levels of happiness, I'll say that y is equal to an intercept plus a slope times x1, and that's your score. Each person will have a score on x1. It'll be either a negative 0.66 if they're in group 1, or 0.33 or 0.3 if they're in group 2 or 3. So it's y is equal to intercept plus slope times your score on x1 plus slope 2 times your score on x2. And your score on x2 is defined by the second contrast. It'll be either a 0, a negative 0.5, or a positive 0.5, depending on what group you're in, plus error. Or I could put the hat on y and say predicted y is equal, I could put the hat here and take the error away and say predicted y is equal to intercept plus slope 1 times x1 plus slope 2 times x2. We could do it that way as well. And the key thing to note is that what I've done is I've created two x variables, two contrasts, where I've assigned numerical values to people for x1, the first contrast, and I've assigned numerical values to people on x2, the second contrast, and I've assigned these numerical values based on this code assignment chart based on group membership determines what your values are for x1 and x2. And then at this point, once I've assigned those values, everyone in my sample now has scores on three variables. Everyone has a score for their level of happiness, how happy they were at the end of the treatment. Everyone in the sample has a score for x1. Everyone has a score for x2. And then I use scores on x1 and x2 to predict y in a regression equation. And to clarify what I'm doing, this slide just shows us how the regression equations would look for someone in group 1, or someone in group 2, or someone in group 3. Because our code assignment chart up here tells us exactly what people's scores will be on x1 and x2, we could plug these x values into our regression equation. So we see that if someone's in group 1, our regression equation for anyone in group 1 will have predicted y, maybe that's their level of predicted happiness at the end of treatment, is equal to an intercept plus a slope 1 times x1, your score on the first x variable. And we know that if you're in group 1, your score for x1 is negative 0.66. So I'll put that right there. And then we take slope 2 times that person's score on x2. And we know that if you're in group 1, there we go, your score on x2 is going to be a 0. So I'll put that 0 right there. So we can use the values, the x values from our code assignment chart and know how that would get plugged into our regression equation. Or if someone's in group 2, we see that the equation for them would be slope 1 times 0.33, because if you're in group 1 or group 2, for people in group 2, your score on x1, on the first x variable, is 0.33, plus slope 2 times negative 0.5, because if you're in group 2, your score on the second x variable is negative 0.5. And for people in group 3, the equation becomes intercept plus slope 1, again, times 0.33. Whoops, there we go. Because if you're in group 3, your score on x1 is 0.33 plus slope 2 times 5, because if you're in group 3, your score on x2 is 5. So that shows you, clarifies how the actual values for x would be plugged into the regression equation for each group. Okay, so that shows you what I'm doing. Now let me start to explain why I'm doing it this way and what we get from it. What's the value of doing this type of coding that I'm talking about? Now, one thing you may be wondering is, why was I using those unusual numbers like 0.33 and negative 0.66? Why not use values like zeros and ones like we've been doing before? Like before, we talked about if I have just two groups, I could say the treatment group is group 1, the control group is group 0. And actually, let me give a name to that when we do coding, when we assign values to people based on group membership, and if those values consist of zeros and ones, when we're using zeros and ones to do our coding, oftentimes people call that dummy coding. So dummy coding is when you're assigning values to people, and the values you assign are just zeros and ones. And as we saw in our previous unit, when we were doing simple contrasts, dummy coding can work very well in some situations. It worked very well for doing simple contrasts. But now that we're going on to a situation where we want to do multiple contrasts, where I have more than two groups, dummy coding, there actually are ways we could use it, but it's going to be more limited and not as useful. So dummy coding is more of limited use for some more advanced analysis. So the thing that I'm showing you is something that's going on beyond dummy coding, where we use zeros and ones, to something more advanced. Specifically, the thing that I'm showing you here is something called orthogonal contrasts. And there's actually many different ways to do coding. There's dummy coding, there's orthogonal contrasts, and there's many other ways that we can do coding. I'm going to focus here on orthogonal contrasts because they are especially useful in situations where we have more than two groups and we need to make multiple contrasts. So orthogonal contrasts are a specific approach to doing coding. Just like dummy coding is one approach to doing a coding that involves the use of zeros and ones, orthogonal contrasts is a different approach to doing coding, to assigning numerical values to people based on group membership that can then be plugged into a regression equation. And orthogonal contrasts, as we will see, is more useful than dummy coding, especially when we have more than two groups and need to make multiple contrasts. And to do this thing called orthogonal contrasts, we have to follow several rules, and I'm going to tell you about those rules in just a moment. And at the bottom here, I have my slide from people thinking about doing orthogonal contrasts, or at least I think the guy in the center, he's thinking about orthogonal contrasts. Maybe this guy over here is confused, and she's thinking about lunch, maybe. I don't know. Actually, I think the original picture labeled this as it was a wedding, and I don't know if it's a wedding. I'm not exactly sure who's marrying whom, but I was thinking maybe they're thinking about orthogonal contrasts. So anyway, let's look at what are the rules for doing orthogonal contrasts, and then what do we get when we do orthogonal contrasts? So the first rule for doing orthogonal contrasts is that when you assign values to people based on group membership, the values you assign for the contrast have to add up to 0. So note, that's what I did in this example. I took group 1 was negative 0.66, group 2 was positive 0.33, group 3 was positive 0.33, negative 0.66 plus 0.33 plus 0.33, that adds up to 0. And for our second contrast, we have a 0, a negative 0.5, and a positive 0.5, and again, that adds up to 0. So when you're doing orthogonal contrasts, one rule we need to follow when assigning the values to people is that the values for each contrast need to add up to 0. And the second rule that we need to follow when we're doing orthogonal contrasts is that for any two contrasts, the sum of the products must add up to 0. Now, if we have three groups, then the number of contrasts we make will be equal to number of groups minus 1, which will be 2. So because we have three groups, we're only doing two contrasts. Of course, if we had more than three groups, we'd need to make more than two contrasts. But with just three groups, we're doing just two contrasts. And so for these two contrasts, the sum of their products must add up to 0. So for example, if you look at, here's people in group 1, we have a score of negative 0.66 for our first contrast and 0 for the second contrast. If we take negative 0.66 times 0, that's actually going to equal 0, but I'm going to put that right down here, negative 66 times 0. And then for group 2, we have the products of their two contrasts will be 0.33 times negative 0.5. So the product of those two values, put that right here. And then for group 3, the product of these two values, 0.33 times 0.5, and put that right there. So if we get negative 0.66 times 0, that will be 0. Then 0.33 times negative 0.5 plus 0.33 times positive 0.5, that will equal 0. And sum it all up, it will sum to 0. So this is showing you a situation that for these two contrasts, the sum of the products adds up to 0. And that satisfies one of the rules for orthogonal contrasts. Note that there's a few different ways we could still make this work. The numbers don't have to be exactly like this. For example, we could switch around which of these for our second contrast. Maybe we could say group 2 gets a positive 0.5 and group 3 gets a negative 0.5. And we could switch the positive and negative, and we would still get the sum of the products would still add up to 0. Or, for example, we could switch some columns. We could say this group 1 gets the negative 0.66 and 0. Group 3 gets a positive 0.33, positive 0.5. We could switch these two around so that group 1 gets the 0.33 and 0.5, and group 3 gets the negative 0.66 and 0. We could switch those columns around. So there's a few ways we could change things around, but we're fairly limited. We don't have a whole lot of options of ways that we could rearrange these numbers and still satisfy this rule that for any two contrasts, the sum of the products must add up to 0. So what do we get if we follow all these rules and create orthogonal contrasts? That is, the first rule is that the number of contrasts we create should be equal to the number of groups minus 1. And the second rule is that for any given contrast, the sum of the values needs to add up to 0. And the third rule is that for any two contrasts, the sum of the products needs to add up to 0. So those are the three rules we've talked about. And if you follow those rules, you will create orthogonal contrasts. So what does that do? Well, one thing to note is that when you create orthogonal contrasts, if you also happen to have an equal number of people in each group, the correlation between those two contrasts will be exactly 0. So note that when you create contrasts, we're creating variables. We created one variable called x1, which was created by assigning values to people based on group membership. We created a second variable called x2, which was created by assigning values to people based on group membership. So we could calculate the correlation between these two variables. And if we have an equal number of people in every group, the correlation between these two variables will be exactly 0. It always will be if you create orthogonal contrasts. Now, usually we don't have exactly an equal number of people in each group, so usually this correlation isn't exactly 0. But if you did have an equal number of people in each group, the correlation would be exactly 0. And, by the way, that is where the name orthogonal comes from. If you were wondering what I mean by orthogonal, orthogonal means to have a correlation of 0. If I say two variables are orthogonal to each other, that's just a fancy way of saying these two variables are uncorrelated. They have a 0 correlation. The word orthogonal comes from the word ortho, which means to be at right angles to something. So, for example, if you go to the orthodontist, that orthodontist puts your teeth at right angles to each other. And we can represent correlations by drawing lines like an XY axis. We can depict, like if here is X and here is Y, and if I draw my X and Y lines at right angles to each other, that could be a way of depicting a correlation that's exactly 0, because with this picture, as I go up and down on X, imagine I'm going higher or lower on this X variable. As I go up and down on X, I'm not changing my level of Y. And if I go up and down on y, I'm not changing where I am on x. So these two lines at right angles to each other could depict a correlation that's 0 because your score on y is unrelated to your score on x. In contrast, if I draw two lines that are kind of in this oblique angle, and maybe this one here is x and this one over here is y, but now as I go up and down on y, I'm also going up and down. Here I'm higher on x as well as higher on y. Down here I'm lower on y, but I'm also lower on x. And if I go up and down on x, I'm also going up and down on y. So if I draw two lines that are oblique like this, that's representing a non-zero correlation. I'm showing some degree of correlation between x and y. If I draw my two lines at right angles, I'm showing a 0 correlation. So when you draw two lines at right angles, we could say that's orthogonal, and that's why we can use the word orthogonal. It's a fancy word in statistics simply to say two things have a 0 correlation. So when we're talking about orthogonal contrasts, it's just a fancy way of saying that if you had equal numbers of people in each group, the correlation between these two contrasts would be exactly 0. Now, I suppose that tells you where the name orthogonal comes from, but I really haven't yet told you why orthogonal contrasts are important. So here is why they are important. So recall to our previous video when I talked about how we can calculate this ANOVA table, and we can plug in values. We can calculate the total sums of squares and the within groups sums of squares based on how far people deviate from their group means, and the explained variance or between group sums of squares, which is based on how far group means deviate from the grand mean. And we talked about how we can calculate the total variance sums of squares, the error variance sums of squares, and the explained variance sums of squares. And we can take explained divided by total to get our eta squared, or percent of variance explained. And then we could fill out the rest of the table and calculate our f value. Now, if we do orthogonal contrasts, if we make two orthogonal contrasts, and I plug them into a regression equation where I use x1 and x2 to predict y in a regression equation, and then calculate this ANOVA table based on this regression equation right here, I will get the exact same result. The results from the regression equation based on orthogonal contrasts will be identical to the ANOVA table we get if we do the group comparisons approach that I talked about in the previous video. We'll get the exact same thing. When we calculate our total percent of variance explained, we'll get the exact same percent of variance explained. And when we calculate our f value, we'll get the exact same f value. So this is simply an alternate way of answering that omnibus question where we calculate the total percent of variance explained and get a significance test for that percent of variance explained. And the value of doing this alternate way of answering the omnibus question is the fact that along the way, we get values for these beta weights, which are going to help us answer a focused question. So it's like in one swoop, we're both answering an omnibus question and we're answering focused questions. Whereas the method I talked about in the previous video, where we calculated this ANOVA table, it did answer the omnibus question, but that didn't really provide a way to answer focused questions. So by calculating these orthogonal contrasts, it allows us to plug our contrast into a regression equation, and we get correct results for our ANOVA table. If I didn't follow the rules for orthogonal contrasts, this wouldn't work. So in order to make this all work, I need to follow these rules for orthogonal contrasts, and then when I calculate my regression equation, I get the correct values for my ANOVA table. And as I was just mentioning, another reason why orthogonal contrasts can be especially valuable is because if I create orthogonal contrasts and I put them into a regression equation, I will get a beta weight for every contrast that I put in my equation. And each beta weight will address an important focused question. The beta weights give me valuable, useful information. And my beta weights will be especially useful if I follow some additional rules. These rules will make our beta weights easy to interpret. So the rule is this: I want each contrast to have exactly two non-zero values. So let's see. So for example, here's our first contrast for x1. And note that there are two non-zero values in this contrast. We've got negative 0.66 is one non-zero value, and 0.33 is the other non-zero value. For contrast 2, for our second x variable, we have one value that actually is 0, so that is a 0 value, and then we have two non-zero values, a negative 0.5 and a positive 0.5. So when you follow this additional rule, it makes your beta weights easy to interpret because each beta weight is going to compare the two non-zero sets of groups. So for example, here's our first contrast for x1, and we've got one non-zero set or one non-zero group. We've got the negative 0.66 group, and then we have the positive 0.33 groups. And so this beta weight for x1 is going to compare. The results for this beta weight will make a comparison between group 1 and groups 2 and 3. In other words, it's going to make a comparison between the control group and the two treatment groups. And then our second contrast has a value of 0 is assigned to group 1. And any group that's assigned a value of 0, that's going to drop out of the comparison. That's not going to be part of the comparison. So the second contrast is going to compare the two non-zero numbers, which is group 2 has a negative 0.5 and group 3 has a positive 0.5. So when I set this up with orthogonal contrast and use these values here, I've created this first contrast that's going to test to see the extent of difference between group 1 on one hand and my two treatment groups on the other hand. And the second contrast is going to test the extent of difference between group 2 on one hand and group 3 on the other hand, because each contrast will compare the two non-zero sets of numbers, and groups assigned 0 are going to drop out of the comparison. And then one final thing that I'm doing in choosing which numbers to use for my contrast is that I'm trying to set my numbers so that each of the two non-zero values in the contrast are exactly or as close as possible to being 1 unit apart from each other. So the distance between negative 0.66 and positive 0.33, negative 0.66 minus positive 0.3, is about, with rounding, it's about 1 unit apart from each other. And the difference between negative 0.5 and positive 0.5 is exactly 1 unit apart from each other. This is something that people often don't do when they do orthogonal contrasts, but when you do this, it makes our results a lot easier to interpret. So for this class, I always want us to do this, that when we do orthogonal contrasts, we set it so the distance between the two non-zero values we use in our contrast, that the distance between them is always 1 unit apart. So let's see what we get if we create these two orthogonal contrasts and plug them into a regression equation. So again, we have an example here where I have 3 groups. I've randomly assigned people to either my control group, to my regular treatment, group 2, or my enhanced treatment, group 3. And everyone has a score on an outcome variable y, maybe that's levels of happiness at the end of the study. And everyone has a score on x1, the first predictor variable, which is the first contrast, a score of either negative 0.66, 0.33, depending on what group you're in. And everyone has a score on x2, my second contrast, which would be values of 0, negative 0.5, or positive 0.5, depending on what group you're in. And so I take my two contrasts, my two x variables, and I put them in a regression equation predicting y. So I have predicted y hat, that's the predicted level of, say, happiness at the end of the study, is equal to an intercept plus slope 1 times a person's score on x1, which is a score for this first contrast, plus slope 2 times a person's score on the second contrast, and that's the regression equation. And so when we run our analysis, we'll get output. We'll get our intercept, we'll get a value for what that intercept, and we'll get a value for our first slope, and we'll get a value for our second slope. And so that's the output we will get when we estimate this regression equation. We'll get 3 parameter estimates. We'll get the parameter estimate for our intercept and for our 2 slopes. And what do those parameter estimates tell us? What do we learn from them? How do we interpret what those parameter estimates are when we plug our orthogonal contrast into the regression equation? So this intercept, beta naught, is the expected y when all x variables are 0. Now I've set it up so that 0 is now a midpoint. So 0 is a balancing point between the groups. So what that means is that it's essentially a type of an average, but actually what this is, it's going to be the unweighted grand mean of y. In other words, it's going to be the mean of the means. If I take what's the mean for group 1, plus the mean for group 2, plus the mean for group 3, and divide by 3. What I mean by unweighted is that I'm not paying attention to sample size. So if group 1 is a really big group and group 2 is a small group, I'm not giving group 1 more weight because it's bigger, and I'm not giving group 2 less weight because it's smaller. I'm just taking the means for my 3 groups, adding them together and dividing by 3 to get the mean of the means for the outcome variable y, which is the level of happiness. So it's the mean of the means for the outcome variable y. And this slide is just showing you the formula that we use to calculate that intercept. Like I was saying, we take the mean for group 1 plus the mean for group 2 plus the mean for group 3, and then divide that by 3 to get the mean of the means. And so our symbol out here, we can have y with 2 bars on top of it, which we could maybe call that, I don't know, call that y bar or something like that. In other words, the mean of the means. And just clarify here that when we're not weighting the group by the sample size. So if group 1 has more people in it, maybe group 2 has fewer people in it, we're not paying attention to how big the groups are. We're just averaging their means to get the mean of the means. Or we can call that the unweighted grand mean. And when I say unweighted, that's that part where we're not paying attention to how big groups are. We're not weighting groups by their sample size. We're just averaging their means. And so we can call this the mean of the means or the unweighted grand mean, 2 ways of describing what this intercept tells us. Now let's look at our first beta 1, our first slope here. What does that tell us? So as always in regression, a beta tells you what's the expected increase in y given a 1 unit increase in x. So in this situation, what does a 1 unit increase in x mean? Well, for x1, a 1 unit means we go from negative 0.66 to positive 0.33 is a 1 unit increase. So this beta right here is going to tell us how much does y go up? How much does your happiness go up if we shift from group 1, which is the control group, to one of our treatment groups, either group 2 or group 3. So beta 1, it tells us the increase in y when x1 increases by 1 unit, which is telling us how much the treatment groups exceed the control group. If we put our 2 treatment groups together in one set, how much is our treatment groups, how much do they exceed our control group? And our beta 1, our first beta, will tell us that. And here's the formula for calculating this first slope for beta 1, where we take the means of our 2 treatment groups, group 2 and group 3, that's our 2 treatment groups, and we add those means together and divide by 2 to get the average mean for these 2 groups. So that's our treatment group mean, or the mean of the means for our treatment groups, and then we subtract from that our control group mean, the mean for group 1, to get the difference between the means for our treatment groups versus the mean for our control group. So again, that's going to tell us how much our 2 treatment groups exceed the control group mean. And so that's the equation that we would use to calculate that first slope, beta 1, to get the difference between our treatment groups on one hand and the control group on the other hand. Note that in this equation, I took my treatment group means and subtracted from it the control group mean. And you might wonder, why did I do it in that order and maybe not flip the order? Why not take, say, the control group mean and subtract from that the treatment group means? And if you do that, you'll get the exact same magnitude of difference, but it will flip the sign. And the sign actually is somewhat arbitrary. and in many situations it doesn't make a difference. But when you're entering answers, say on homework, on Canvas, sometimes it's important to have the correct sign. So it would be useful to know what is the correct way to do it. How do you decide? Do you do treatment means minus control group mean, or do you do control minus treatment? What order do you put this in? And here I have a basic hint. You can follow this. If you do this rule, you will always get the correct sign. And that is this. You take whatever groups are assigned the positive code and subtract from it the group assigned the negative code. So we take the groups assigned the positive code minus the groups assigned the negative code. So in this case, groups 2 and 3 were assigned a positive code, so I put that first. And group 1 was assigned a negative value, negative 0.66, so I put that second. So if you follow this rule, take whatever groups were assigned a positive code, that's the first value you put in your equation, minus the groups assigned the negative code, that's the second thing you put in your equation. If it's the positive code groups minus the negative groups, then you will always get the correct sign, which will give you correct answers if you're entering things on Canvas and it pays attention to positive and negative signs. Now let's look at our second beta, beta 2. If we run our analysis and get results for beta 2, how do we interpret what beta 2 means? What does beta 2 tell us? So again, anytime we're doing regression, we can say the beta weight tells us what's the expected increase in y when x goes up by 1 unit. In this case, it's x2. So what's the expected increase in y when x2 increases by 1 unit? And as it turns out, this is going to give us the difference between the two treatment groups. Note that group 1, our control group, is going to drop out of this contrast. Here's our equation down here. If you're in group 1, the equation, our regression equation, becomes predicted y, so that your predicted happiness is equal to intercept plus slope 1 times negative 0.66 plus slope 2. This is our second beta we're looking at right now. Slope 2 times 0, and slope 2 times 0 will be 0. So that's just for people in group 1, that slope is going to drop out of the equation. That will just become 0, and that drops out. So essentially what this means is that people in group 1 are being left out of this contrast, and we're going to end up comparing people in group 2 with people in group 3. Our two treatment groups is what this contrast will compare. Specifically, the value for beta 2 will simply be the mean for group 3 minus the mean for group 2. The mean for group 3, that's our enhanced treatment group, minus the mean for group 2. In other words, the difference between our two treatment groups. Just the mean for group 3 minus the mean for group 2 will give us what beta 2 is telling us. It's giving us the size of difference between those two groups. And as before, it could be useful to pay attention to which group is getting subtracted from which group. In this case, I have the mean for group 3, and I'm subtracting from that the mean for group 2. Now we could have done it the other way. We could have taken the mean for group 2 minus the mean for group 3, and that would flip the sign from positive to negative or negative to positive. We'd still have the same magnitude of effect. It would still be the same basic meaning. But if you were entering answers on Canvas, where Canvas was paying attention to the positive or negative sign of the value, then you'd get the wrong answer if you did it in the wrong order. And again, to get the correct order, take the groups assigned a positive value minus the groups assigned the negative value, and it will come out right. So in this case, we're looking at the difference between group 2. For the second contrast, group 2 was assigned a value of negative 0.5, and group 3 was assigned a value of positive 0.5. So we take the group assigned the positive code, which is group 3, minus the group assigned the negative code, which is group 2, and we will get the correct value for that beta weight. For this unit, I'm focusing on just one particular way of doing orthogonal contrasts when we have just 3 groups. Note that there are other ways of doing orthogonal contrasts. That is, there's other ways of assigning numerical values that meet all the criteria for orthogonal contrasts. And if we have more than 3 groups, then we need to have more contrast. For example, here if I have 4 groups, maybe group A is the pea group, and group B is the tomato group, and C is the spinach group, and D is the carrot group. I'm not sure, maybe these are groups that were fed different types of vegetables and they were measuring some kind of outcome variable. So here I have x1, this would be a contrast that goes 0.5, 0.5, and negative 0.5, negative 0.5. So we're comparing groups A and B with groups C and D for that contrast. And then contrast 2 is positive 0.5 and negative 0.5 and 0 and 0. So that's going to compare group A with group B. And then the third contrast is 0, 0, positive 0.5, negative 0.5. That's going to give me a value that will compare groups C and D. So if we put these three contrasts into our regression equation, our first beta weight would tell us the size of difference between, on one hand, groups A and B, and on the other hand, groups C and D. And our second contrast would tell us the size of difference between group A and group B, and C and D would drop out. And the third contrast would tell us the size of difference between group C and D, and groups A and B would drop out. And if you were to look at it, this actually follows all the rules here. Note that for each contrast, if you add up all the values for each row, they all add up to 0. And in this case, if you pick any two, we could take the sum of the products for x1 and x3, 0.5 times 0 plus 0.5 times 0 plus negative 0.5 times 0.5 plus negative 0.5 times negative 0.5. If you add up all those products, that would add up to 0. We could take any two contrasts. We could take, say, contrast x2 and x3, 0.5 times 0 plus negative 0.5 times 0 plus 0 times 0.5 plus 0 times negative 0.5, and that the sum of those products adds up to 0. So we could take any two pair of contrasts, and the sum of the products would add up to 0. So this meets the rules for an orthogonal contrast. This just gives you an example of something we could do if we had 4 groups. And of course, there's other ways we could arrange our values and still meet the criteria for orthogonal contrasts. So now let's put everything together that we've been talking about in this unit on doing multiple contrasts. So say I'm doing a study and I have students that are suffering from statectomy sadness, and I randomly assign students to 3 groups. One group goes to my control group, and another set of students get this regular green gas happy therapy, aromatherapy, and a third group gets the enhanced version, the green gas happy aromatherapy plus coffee. So students get randomly assigned to 3 groups, and we do our analysis, and in our analysis we can address 2 questions. One question is the omnibus question. Overall, is there a difference between groups? And another question is the focused question. If we, for example, compare the control group with our 2 treatments, is there a difference? Or if, for example, if we compare treatment A with treatment B, our regular treatment with the enhanced treatment, is there a difference between those 2 treatments? And those would be focused questions. So we do our analysis, and we want to address omnibus questions, and we want to address focused questions. And you now have everything you need to address both those types of questions. And in each case, you'll want to be able to identify what is the effect size, what statistic will you use to give you an effect size that will address the particular question you want to address, and what is the inferential statistic you can use to test the significance of that effect size. So for the omnibus effects, if you want to know overall, is there a difference between groups? We talked about that in the previous video. Our effect size is eta squared, the percent of variance explained. The percent of variance in the outcome variable, in this case happiness, the percent of variance in happiness that's explained by group membership. And we have our ANOVA table, and we calculate our explained variance, or what is typically called between groups variance when we're doing group comparisons. Explained variance, or between group variance, divided by total variance, sum of squares explained, divided by sum of squares total, to get the percent of variance explained. And that is our eta squared, that's our effect size. And we test the significance of our eta squared with our F statistic. Our F test will tell us if we get an F test, we calculate the p-value for our F statistic. And if the p is less than 0.05, then we say we have a significant effect. We have a significant difference between groups. Now at this point, this is the omnibus effect. So this doesn't tell us which group is different from which group. It just tells us that somewhere in here, there is some degree of group difference. So our eta squared with an F statistic tests the omnibus effect and tells us to what extent is there a difference between groups. In general, overall, to what extent is there a difference between groups? So what about the focused questions that we need to address in this analysis? For example, one of the focused questions we need to address is whether there's a difference between our control group and the two treatment groups. And another focused question is whether the two treatment groups are different from each other. What are the statistics that we will use to evaluate these focused questions? So for a focused question, our effect size will be the D statistic. It will be Cohen's D. That will be our statistic to use to give us an effect size to address the focused question. And this is the same thing we used back in our unit when we were looking at simple contrasts and we were looking at a difference between just two groups. And recall then I said our effect size would be just the D statistic, would be by default. That would be the easiest effect size to interpret, which is going to be the same thing here. By default, our effect size will be a D statistic. And here I have just a review of the formula for the D statistic. This is just a review from our previous unit of how we calculated it. So recall the D is equal, we take the mean for group 1 minus the mean for group 2, the difference between the means, divided by the pooled standard deviation. And over here I have the formula for the pooled standard deviation. That is, we're essentially averaging the standard deviations together for our two groups, although we're weighting it by sample size in this case. So the groups with larger samples with more degrees of freedom carry more weight. So we take the sum of squares for group 1 plus the sum of squares for group 2 divided by the sum of the 2 degrees of freedom, take the square root, and we have our pooled standard deviation, essentially the averaged standard deviation for our two groups. And so we then take our difference between means divided by the pooled standard deviation to get our D statistic. And that is how we did it when we had just two groups. Now, in our current example, where we have more than two groups in our study, I'm going to make a slight change to how we calculate the D statistic. So if I say I have three groups, I have group 1, maybe group 1 is my control group, put a little C here for our control, and then maybe I have treatment A and treatment B. Maybe it's treatment A is the regular treatment and treatment B is the enhanced treatment. So I've got three groups, control group and two treatment groups. And maybe I want to address the focused question of, is group A different from group B? Are these two groups different from each other? And so if I follow the normal procedures for a D statistic, I would get the mean for group 1 minus the mean for group 2 divided by the pooled standard deviation for these two groups. But one thing to note is that when we do this analysis, one of the assumptions we make is that all these groups don't differ from each other in terms of their variances, in terms of their standard deviations. If you recall from our unit when we were talking about just doing a simple contrast, looking at a difference between two groups, that was one of the assumptions of the t-test we talked about, was the homogeneity of variance, the assumption that each group has the same variance, or each group has the same standard deviation. That groups might have different means. One group might be really happy, one group might be not so happy, but the spread of their happiness scores, the standard deviations of their happiness scores, each group should have approximately the same spread of standard deviations. So that means that the standard deviation for group A should be about the same as the standard deviation for group B, and it should also be about the same as the standard deviation for group C. And if we want to estimate what the true population standard deviation is, if we assume that all groups have the same standard deviation, we would get a better estimate of that standard deviation if we average all three of these groups together. Even though if right now I'm wanting to compare treatment A and treatment B, my two treatment groups, and I'm not, group C, my control group, isn't actually part of this comparison, but even though the control group's not part of that comparison I'm focusing on right now, if I include the standard deviation of my control group and estimating the actual standard deviation for my D statistic, presumably if I include my control group in estimating the standard deviation, I will get a more accurate estimate of that standard deviation than if I exclude it. So what this means is we're going to calculate a D statistic, I'll take the mean for one group minus the mean for the other group, and rather than dividing by the pooled standard deviation for just those two groups, I'm going to take all the groups in my analysis, all the groups in my study, whether they're included in this comparison or not. I'll take all the groups in my study and get the pooled standard deviation for all the groups in my study. And what is that pooled standard deviation? That is the pooled within group standard deviation. Now, if I say that, that should sound a little bit familiar. Where have you heard that word before? The pooled within group standard deviation. It's essentially the average within group standard deviation across all your groups. Recall from our previous video, we talked about that ANOVA table, and if we calculate the standard error of estimate, that is, we take our square root of our mean squared error, this was in our previous video, I talked about this. If we take the square root of our mean squared error from our ANOVA table, that gives us our standard error of estimate. The standard error of estimate is how far on average do people deviate from the predicted values. But when we're doing group comparisons, people's predicted values are their group means. So the standard error of estimate, how far on average people deviate from the predicted values, is the same thing as how far on average people deviate from their group means, which means that the standard error of estimate is the same thing as the pooled within group standard deviation. So if we go to our ANOVA table and get that mean squared error value from our ANOVA table, take the square root of that, that will give us what in previous units we've called the standard error of estimate, but now I'm saying that's actually the pooled within group standard deviation. So again, our standard error of estimate, we can get that from the ANOVA table, taking the square root of the mean squared error from the ANOVA table, and that's the same thing as the pooled within group standard deviation for all groups. And that is how we will calculate the D statistic. If anytime I have a study that I have more than two groups, I'll get the difference between means divided by the standard deviation pooled not just across two groups, but across all groups in my study. And I can get that simply by going to the ANOVA table, getting the mean squared error, taking square root of that, and that gives me an easy way to calculate a D statistic in situations where I have more than two groups. So putting this all together, it means that a D statistic would actually be quite easy to calculate from the results we get from a regression analysis. So for example, one of our focused questions involves our first contrast, which is the difference between our control group on one hand and the two treatment groups on the other hand. And this beta right here, beta 1, as we saw, is given by this formula right here, which is the difference between, on the left-hand side, we have the mean of the two treatment groups and our control group. It's the size of difference between our treatment groups and our control group. And so to convert that to a D statistic, we take that difference, which is given by this beta weight right here. That beta weight gives us the size of difference between those two groups that we're comparing. So we take our beta weight, which gives us the size of difference between two groups, and we divide it by the square root of mean squared error, and that will give us our D statistic. So to calculate a D statistic, all we need to do, we need to get the beta weight from our regression output, divide that beta by the square root of the mean squared error, and that will give us our D value, the extent of difference between our control group and our two treatments in standard deviation units. And then for our second contrast, for beta 2, recall that beta 2 is giving us the size of difference between our two treatment groups, our regular treatment and our enhanced treatment, the mean for group 3 minus the mean for group 2. And so if we take that beta 2, the size of difference between those two groups, divide by the square root of the mean squared error, which is our pooled within group variance, we get the D statistic for that second contrast. So now at this point, we can calculate two D statistics, one D statistic for each of the focused questions we're addressing. That is, one D statistic for each contrast. We have one contrast between the control group and our two treatments. And this D statistic, our first D statistic, tells us the size of difference between those two groups in standard deviation units. And then we have a second contrast, which is comparing our two treatments, the regular treatment versus the enhanced treatment. And this D statistic will tell us the size of difference between those two groups in standard deviation units. So we have two contrasts, that is two focused questions, and we have a D statistic for each contrast. And the D statistic is the statistic we use to address that question about effect size. And finally, how do we test the significance of our two D statistics? Well, we will test significance with a t-test, and we will simply use the t-test for our beta weight, because the beta weight and the D statistic are both giving us information about the same effect. The beta weight tells us what is the size of difference between, say, the control group and our two treatments, just in raw score units. And then when we convert our beta to a D statistic, when we divide it by the square root of our mean squared error, it turns it into a D statistic, which gives us the size of difference between the control group and our two treatments in standard deviation units. But it's still the same effect either way. So the significance of our beta is the same thing as the significance of the D statistic. So we can just do a t-test for our beta weight, or we take our beta weight divided by its standard error. As always, a t-test is always a statistic divided by its standard error. So we take our first beta divided by its standard error and get a t-test for that beta weight. And whatever the t value is for that beta weight, it's the same thing as the t value for our D statistic, because they're both testing the same effect. So if this beta has a significant t value, it means we have a significant difference between groups. And then we can do a t-test for the second beta and determine if that's significant. So putting it all together, we're looking at a situation where I have 3 groups, a control group and 2 treatment groups. And in this type of study, I can address an omnibus question of overall, is there a difference between groups? And my effect size for the omnibus question is the eta squared, percent of variance explained. And my inferential statistic to test the significance of eta squared is the F test. And then in this case, I have 2 focused questions that I'm addressing. One question is whether the control group differs from the 2 treatment groups. That's one focused question. Another focused question is whether the 2 treatment groups differ from each other. And I test both those focused questions. The effect size will be the D statistic. And I'll test the significance of each D statistic with a t-test, where I simply take the beta divided by the standard error of the beta. And that is everything for this section on doing planned contrasts. So the next question then is, what if you're doing a research study and you have more than 2 groups, but you want to address research questions that can't be addressed if you're limited to doing orthogonal contrasts? For example, what if you're doing a study and you have 3 groups and you want to make all the possible comparisons between groups you can make? Maybe you want to compare group 1 with group 2, and you want to compare group 1 with group 3, and you want to compare group 2 with group 3. You want to make all the possible comparisons. And as we saw, if you're following the rules for orthogonal contrasts, you can't make all the possible comparisons. So what do you do if you want to make all the possible comparisons you can make? In that case, we're going to do something called a post hoc analysis. A post hoc analysis is an approach to answering focused questions that are more flexible than using orthogonal contrasts and will allow us to make all the possible comparisons. So, how do we do post hoc analyses? Well, I will save that for another time.